Hey guys, Mr. Betts here. In our last unit, we talked about differentiating inverse functions generally. And so in this unit, I want to talk specifically about how we're going to do that with particular trig functions. So we're going to look at the 6 basic trig functions and how we would take the derivative of them. I did talk about this a little bit in the last video, or at least the last topic, but I want to talk more specifically about how we get the inverse trig functions to begin with, because that is going to come into play when we're actually taking the derivative. So bear with me here. So remember, if we want the inverse sine function, what we're going to do is we're going to switch the x and the y, and then we're going to solve for y. So remember, graphically with inverse functions, what that means is we're going to take the graph of the function and we're going to flip it over the line y equals x. It turns out with all of the trig functions, this new function, the flipped version, does not pass the vertical line test. So we're going to have to look at domain and range restrictions so that we can handle that. So with the sine function in particular, the sine function has a domain of all real numbers. So we can plug in any x value for x in the sine function, and we get a value that ends up being between -1 and +1. That means that when we take the inverse, our domain and range are just going to flip because we're flipping x's and y's. Domain is possible x values, range is possible y values. So our domain and range are the opposite. However, because we have to restrict the domain, then we're also going to then restrict the range of the inverse sine function. So remember, for a function to be invertible, it has to be what we call 1-to-1. And graphically, what that's going to look like is it has to be strictly increasing or strictly decreasing. So what we do is we take the sine function and restrict it just to values starting at -π/2 and including -π/2 and going up to +π/2. So we're just looking at the sine function in the 4th quadrant and in the 1st quadrant. So 1st quadrant would be here, 4th quadrant would be here. What we end up doing when we use the inverse sine then is if we have an angle that would be in the 2nd quadrant or 3rd quadrant, we have to understand the situation and understand that a value that we get in the 1st quadrant could actually represent an angle in the 2nd quadrant. But by making this restriction, then we eliminate some of the inverse and we get what ends up being a function that passes the vertical line test. Okay, so let's say we actually want to take the derivative. We've talked about how to take derivatives of inverse functions and corresponding points and stuff like that. So let's talk specifically about the sine function. If I want to take the derivative of the sine function here, the first thing I'm going to do is I am going to rewrite it as, instead of y equals the arcsine of x, I'm going to write it as the sine of y equals x. All right, so with the restrictions that we have on domain and range, these two right here, or at least, this is going to be the inverse function for the sine function. So now I'm going to take the derivative of both sides of this using implicit differentiation. So implicit differentiation is a good tool that we can use when we're dealing with inverses, and it actually allows us, outside of trig functions, because we're restricting trig functions, but it allows us to take derivatives and do derivative stuff on equations that are not functions. So we could actually use implicit differentiation to get derivative information about an unrestricted inverse to sine at any point. But that's besides the point right now. We're gonna keep that restriction on there, and so we're gonna take the derivative on both sides. Derivative, what we're looking for here is a slope. So we want dy dx. So we're taking the derivative with respect to x. So derivative of sine is cosine, but that y is not an x, but we're taking the derivative with respect to x. So it's going to be a baby function or an inner function, and we have to multiply by the derivative of y with respect to x. On the right side, the derivative of x is going to be 1. And so we get dy dx is equal to 1 over cosine of y. Now, when we were dealing with inverse relations or taking the derivative using implicit differentiation, we saw examples where the derivative had maybe other derivatives in it or had x's and y's in it, or in this case has a y in it, and that was okay. But now what we're doing is we're taking the derivative of a function in terms of x, so we should get an answer that's also in terms of x. So what I'm going to do here is I'm going to use some trig properties to get rid of this y here. And more specifically, I'm going to get rid of the cosine of y all at once. So I'm going to use a triangle because remember, all of trigonometry is based on triangles, specifically right triangles. And so this expression right here gives us information that we can use to figure out what this triangle would look like. So the equation sine of y equals x is telling us the sine of some angle y, which I'm going to label in here, is equal to x. Remember, sine is opposite over hypotenuse. So if we think of this as x over 1, then we can say this is opposite as x and the hypotenuse is 1. Using this triangle, we can also then figure out what the cosine of y is. So the sine of y gave us the triangle setup, but using the Pythagorean theorem, we can figure out that this side is going to be the square root of 1 minus x squared. And the cosine of y in this triangle then is going to be adjacent over hypotenuse. So the cosine of y is going to be the square root of 1 minus x squared. So this derivative then, replacing the cosine of y with that expression, is going to be 1 over the square root of 1 minus x squared. So this right here is just a formula or an equation that we need to know. I will tell you that I'm not going to ask you to memorize this generally throughout the year, but when you take the AP test at the end of the year, it is something that you need to know. Now, we can go through that same process with the other basic trig functions. So I'm going to do that kind of quickly here. So y equals arctangent. What we would do is we would rewrite this equation as the tangent of y equals x. We could take the derivative on both sides. We can solve for dy dx. We can set up a triangle, and we can substitute for the y value that we get in our derivative and get an x value, and that's going to give us this one. And I'm going to have all of these on the last screen, so you don't need to write them down yet. Same thing with secant. So we can take this equation right here and we can rewrite it as the secant of y equals x. We can use implicit differentiation to take the derivative of both sides with respect to x, solve for dy dx, replace the y that we have in that expression. And this one looks a little bit different. It has an absolute value here, and there's a math reason for it, and then there's a justification for it that I'm going to give you. If you look at the graph of the secant function, you can see that all tangent lines are going to have positive slopes. So no matter what we plug in for x, we should get positive slopes. So that's kind of a graphical justification that absolute value should be there. The mathematical reason that we get an absolute value has to do with when we draw our triangle. In analytic geometry, the hypotenuse is always going to be positive. So where x values could be positive in the first and fourth quadrant, or x values could be negative in the second and third quadrants. So x and y could both be positive or negative. The hypotenuse is always going to be interpreted as positive. So anyway, you don't need to understand where the absolute value comes from, but understand that it is there. With the cofunctions, so if we want to find the derivative of arc cosine or arc cotangent or arc cosecant, we're going to use a property that you probably aren't real familiar with, but it's actually how the cofunctions came about. And that is that the sine and the cosine are well, let me back up here. Cosine means that it's the sine of the complementary angle. So complementary being that we add together to get 90. So the idea with cosine, and this is just a little historical lesson here, the sine of theta is opposite over hypotenuse. So the sine of theta is x over h. Well, cosine of some angle means that it's the sine of the complementary angle. So if I want to know the cosine of alpha, that's the same thing as the complement, or the sine of the complement to alpha. And the complement to alpha is theta, because in a triangle, the angles add up to 180, then the two non-right angles are going to add up to 90. So these two angles are complementary. And so long story short, when we take the arc sine and the arc cosine, we get pi over 2, which is the radian version of 90 degrees. So this is just an expression saying that sine and cosine are the sine of complementary angles added together. Okay, so if we take the derivative of this expression, the derivative with respect to x of arc sine of x, plus the derivative with respect to x of arc cosine of x is equal to 0, because the derivative of pi over 2 is derivative of a constant, which is 0. What that means is these are actually opposites of each other. Whatever the derivative of arc sine is, the derivative of arc cosine is just going to be the opposite, so that when we add them together, we get 0. So where the derivative of arc sine is 1 over the square root of 1 minus x squared, the derivative of arc cosine is going to be the opposite of that. Now, the point of all of that is that for arc cosine and arc cosecant and arc cotangent, cosecant and cotangent are just the secant and tangent of the complementary angles. Then this same equation is going to be true for arc secant and arc cosecant, and it's going to be true for arc tangent and arc cotangent. And so each of the derivatives of the arc cofunctions is just going to be the opposite of the derivatives of the arc functions. So long story short, I had a triangle there to help me. Didn't use it. Long story short, if we can remember the derivative of arc sine, then the derivative of arc cosine is just the opposite of that. And same thing is true for tangent and secant. So again, you need to be familiar with these. You need to be familiar with the form of these, especially later on when we start doing the opposite of differentiation, so anti-differentiation. We need to be able to see an expression that looks like this and say, hey, if we took the derivative of arctangent, we would get that. So you need to be familiar with it. I'm not going to ask you to memorize it until we get closer to the end of the year and the AP test.